Hi guys, today we will talk about chapter 5, which is the topic is about digital to analog conversion. So basically, digital to analog conversion is the process of changing one of the characteristics of an analog signal based on the information of in the digital data. So in digital to analog conversion, we must have three mechanisms to complete it. The first is ASK, amplitude shifting. Second one is FSK, frequency shifting, and the third one is PSK, phase shifting. So basically, the ASK and PSK can combine together and it will become QAM, which is quadratic amplitude modulation. Okay, there are four aspects in digital to analog conversion. The first one is data element versus signal element. The second one is data rate versus signal rate. The third one is bandwidth, and the final one is carrier signal. So the data element is the smallest piece of information to be exchanged, the bit rate. And the signal element is the smallest unit of a signal that is constant. So the second one is data rate versus signal rate. So this is the relationship between data rate and signal rate. So basically, this is signal rate, this is one is data rate. Okay, in the previous relationship, we can see that there is R here. R in analog transmission, R is equals to log to L. Log to L. Then basically L is not level. L is type of signal element. And in analog transmission, usually the digital data, in the analog transmission of digital data, usually the baud rate is less than or equal to the bit rate. Okay, let's look at the example of data rate versus signal rate. So basically in the example, if we follow the formula, we can see that R is actually 4 and S is actually 1000. So this become like this one, S equals to N times 1 over R baud. So S, they already give you 1000. So equals to N is unknown, times 1 over 4, 4 is the R. So we want to find the N. N is equals to 4 times 1000 baud. N is equals to 4000 baud. There you have it. As for the bandwidth is proportional to the signal rate except for FSK, in which the difference between the carrier signals need to be added. Okay, the last one is carrier signal. Okay, now in analog transmission, the sending device produces a high frequency signal that acts as a base for the information signal. So basically, the base signal is called the signal carrier. More characteristics, which are the three, which are the amplitude, frequency, or phase. This is modulation. That modifying is called the modulation, or in the other name is shift keying.
Amplitude shift keying, ASK, means amplitude of the carrier signal is varied to create signal elements. The frequency and phase remain constant while amplitude changes. In ASK, there are also binary ASK. This is which we can have several levels of signal elements, each with different amplitudes. It is also referred as a binary amplitude shift keying or on-off keying, or called as OOK. The peak amplitude of one signal level is 0, and the other is same as amplitude of the carrier frequency. Bandwidth for ASK shows that carrier signal is only one simple sine wave process of modulations produce a non-periodic composite signal. And they also have a formula which is B equals to 1 plus D times S, which is this one. Okay, and this is the graph for ASK graph. Can you see it? If it is one single element, if it has one signal, it will have a peak, and if it turns to 0, it will become constant. Okay, as you can see, there is a graph for binary amplitude shift keying, and D must be bigger or equal to 0, that related to the condition of the line. And there is also stated there the formula for binary amplitude shift keying, how to calculate. So the formula is B equals to 1 plus D times S, and S equals to N times 1 over R. I will show you how to calculate by using the formula later. Okay, here I show you the calculation of the amplitude shift keying. This given question is bandwidth with 100 kHz spans from 200 kHz to 300 kHz. So, what are the carrier frequency and bit rate if modulated data using ASK with D equals to 1. Here, I show you the solutions. You use the formula F equals to N times 1 over R, B equals to 1 plus D times S. Okay, B equals to 1 plus 1 times N times 1 over 1. So hundreds equals to 2N plus 2N times 1. So 100 equals to 2N. So N equals to 50 because we divide the hundreds with 2. Where we get the hundreds, we get from the bandwidth. How to get the bandwidth? B equals to 300 minus 200 equals to hundreds. So we substitute the B with the bandwidth. Alright, now we talk about FSK. FSK is basically the short form for frequency shift keying. Okay. Alright, so frequency of the carrier signal is varied to represent data. The frequency of the modulated signal is constant but changes if the data element change. Peak, amplitude, and phase remain constant. Alright, next we will talk about bandwidth for FSK. So basically there is a formula for this bandwidth of FSK. For the example, we have an available bandwidth of 100 kHz which span from 200 to 300 kHz. What should be the carrier frequency and the bit rate if we modulated our data by using FSK with D equals to 1? Right, so basically this formula is used for example 5.5. So we want to select this one is the
the T just now is, we assume it is 1. So we take the formula is equal to 100. So 2s plus 2 is equals to 100. So we get like this. So we assume this one is equals to 50. So it's basically like 2s plus 50 is equals to 100. So 2s, the 50, we bring it to the other side, so minus 1, so 50 s is equals to 25 kilopound. So we have it. This one is the solution for the example. Okay, now we will talk about implementation of BFSK. In implementation of BFSK, there are two types of it, and the first one is non-coherent. In non-coherent BFSK, there may be discontinuity in the phase when one signal element ends and the next begins. In non-coherent BFSK can be implemented by treating BFSK as two ASK modulations and using two carrier frequencies. The second one is coherent. In coherent BFSK, the phase continues through the boundary of two signal elements, and coherent BFSK can be implemented by using one voltage control oscillator or VCO that changes its frequency according to the input voltage.
Hi, I'm IRSALINA and I will be talking about PSK. First of all, what is PSK? PSK stands for phase shift keying. In phase shift keying, the phase of the carrier is varied to represent two or more different signal elements. Both peak amplitude and frequency remain constant as the phase changes. Today, PSK is more common than ASK or FSK. The simplest PSK is binary PSK, in which we have only two signal elements, one with phase of 0 degree and one with phase of 180 degrees. Okay, I'll show you the graph for PSK. As you can see, the peak is constant. Oh, sorry for the bad drawing. It's constant whether the peak is the same, even whether it's the 1 bit 1 or 0. This is the bandwidth for BPSK. The bandwidth is the same as that for binary ASK but less than that for BFSK. No bandwidth is wasted for separating two carrier signal. This is the example question for the PSK. In PSK, 2 bits carried by one signal element, which means R is equal to 2. So to solve this question, the formula is equal to N multiply by 1 over R. N is equal to 12. So 12 times 1, R equal to 2. 1 over 2 equal to 6. So this is the solution. The implementation of BPSK is simple. The reason is that the signal element with phase 180 degree can be seen as the complement of the signal element with phase 0 degree. This gives us a clue on how to implement BPSK. The polar NRZ signal is multiplied by the carrier frequency. The 1 bit positive voltage is represented by a phase starting at 0 degree. The 0 bit negative voltage is represented by a phase starting at 180 degrees. We use the same idea as we use for ASK but with a polar NRZ signal instead of a unipolar NRZ signal. The advantage for PSK is it is less susceptible to errors than ASK, while it requires the same bandwidth as ASK. In ASK, the criterion for bit detection is the amplitude of the signal, while in PSK it is the phase. Noise can change amplitude easier than it can change the phase. PSK is superior to FSK because we do not need two carrier signal. More efficient use of bandwidth, which means high data rate, are possible compared to FSK. And lastly, the disadvantage of PSK is it has more complex signal detection or recovery process than in ASK and FSK. So that's it from me. Thank you. Bye.
Quadrature amplitude modulation, or also called as QAM. It is the idea of combination of ASK and PSK. Two corners, one is in phase and another one is quadrature. They are also with different amplitude levels for each corner. Possible variations of QAM. There are four simplest. Okay, and for the first graph, you can see it's a 4 different signal elements types, and also ASK and also OOK. Use unipolar and ARSAC signal to modulate each carrier. For the second graph, using polar and ARSAC, same as QPSK, quadrature phase shift keying. And for the third graph, use signal with two positive levels to modulate each of the two carriers. And for the fourth graph, you can see is constellation of a signal with 8 levels for positive and for negative.